Pointers, topic 9.1, getting the address of variable. So before we do that, let's define what a pointer is. A pointer is a variable that stores memory addresses. So you grab a memory address of other variables and you store it in a pointer variable. So the pointer variable points to the address of other variables. So how do I declare a variable and how do I store the address of other variables in it? The key operator is the ampersand operator. This ampersand operator you have seen before using references. So passing a variable by reference, you add the ampersand character. This way you're passing the reference of the variable. In other words, you're passing the memory address of that variable. How do I declare a pointer? You declare a pointer by specifying what data type you are planning to point at, for example, integer. Then you add the asterisk symbol. Then you specify the name. So for example, my PTR. Now this pointer is a variable that points to an integer data type. So it stores a memory address of an integer data type, and it can only store addresses for integer data types because that's what was specified when we declared this pointer. How do I store or initialize a value to this? It's a good habit to start by saying it's equal to null. This way, if I check against my variable and I check if it's null PTR, that means it's not pointing to anything, then I know that it has no value in it. Let's say I have my integer, and my integer is equal to 5. In order to store the address of this integer in my pointer, as I mentioned, I use the ampersand character. So ampersand my integer. This way, if my integer is at address, let's say 1000, then 1000 will be stored in my PTR. So if I display what my pointer holds at this point and the address of my integer, it's going to display the same value. If I run it, we're going to see that my integer is at address this, and the pointer is carrying this address. So this is what the pointer is carrying, and this is the reference of my integer. And notice they are the same. Now, what if I want to, this is called referencing a variable. So I'm referencing a variable through my pointer. In order to access my integer through my pointer and get the value in it, which is 5, get it or set it. So I can access it to read it or access it to change it. I need to dereference my pointer, and I dereference my pointer using the asterisk symbol. So if I say display asterisk my pointer, this will display 5. See the 5? So do not confuse the declaration with dereferencing. If I'm declaring, I use the asterisk, my variable name, and then the value if I want to. If I'm dereferencing, I'm not declaring anything. I'm just dereferencing, basically putting that same symbol in the same fashion before the name. So I can do it like this as well. So it's this in the same fashion, same style, but instead of declaring, I'm just counting. So I'm using it alone with the symbol. This is called dereferencing. This will show me the value that the pointer is pointing to. The same way, dereferencing allows me to change the value in that memory address. So I'm changing the value that the pointer is pointing to from 5 to 10. So if I cout again, it will display 10 at this point. So 5, 10. I was able to access the memory address through the pointer, change its value. One time I accessed it and read the value, and another time I accessed it and changed the value. So the book starts by saying getting the address of a variable. The address operator, which is the ampersand, returns the memory address of a variable. So this fashion, this syntax right here returns the memory address of a variable. And then they draw a figure to show you how the memory address is continuous block of memories. You have a letter, 1 byte, then you have a number, short, and then you have amount, which is an integer. They show you how a letter consumes or allocates 1 byte or 1 slot, short 2 bytes or 2 slots, then amount 4 bytes or 4 slots. And notice the numbers of memory addresses. Letters start at 1200, then number is 1200-01, because a letter is only 1 character. Then the fact that number is short and 2 bytes, then the next address or the next available address is 1203. So 1201 and 1202 are allocated for the integer, for the data type short or the variable number. Then at 1203 we have the number amount or the integer amount, which consumes or allocates 4 slots, 4 bytes. So 1203, 1204, 1205, 1206 are allocated for the integer amount. Pointer variables. Topic 9.2. Pointer variables, which are often just called pointers, are designed to hold memory addresses with pointer variables. You can indirectly, like we did here, you can indirectly manipulate data stored in other variables. Now, the topic continues to show you how to create and use pointer variables. So this is how I created a pointer variable, and this is how I used it. I grabbed the address of another variable. It has to be of the same type. If I have a different data type, it's not going to allow me. For example, short, my short equals 10. If I say, hey, my pointer, I need you to store the address of my short, it's not going to allow me. It's going to say, hey, you cannot do that, illegal. This is different. I'm a pointer that points to an integer, but you're telling me to store a short. You cannot do that. So they have to have the same data type. And I'm going to explain in future why. We saw how we initialize using a null pointer. And if you need any more questions on how this is stored in memory, reach out or read figure 9-4. It shows you how pointer has its own let's call it it's a carrier. So it's a carrier, and you put an address in it. That address is for some variable in the memory that also has a value in it. So the figure shows 9-4, x is at address 0 times 7E00, and that x is carrying the value 25. So the value 25 is at memory 0x7E00. Then PTR, which is the pointer, is carrying that memory address, carrying 0x7E00. And then the example after that figure, which is program 9-3, is very similar to what we just did here. They are declaring a variable and giving it a value. Then they are declaring a pointer, giving it null pointer. Then they are grabbing the address of that variable and storing it in PTR. Then they are displaying stuff. At some point, at the last line, they change the value. They dereference the pointer, putting new value in it, and then counting again. Then they show you that you can do all sort of adding values just like you did in normal variables. For example, I can do the combined assignment. So just like I do with variables, we can just do that. So this will add 10 to the existing value. This is equivalent to saying my pointer dereferenced equals my pointer dereferenced plus 10. So my pointer dereferenced is 5, just how we saw here. 5 plus 10 will be stored in dereferencing my pointer, meaning go to the memory address and put that value in there. Then they try to explain the relationship between arrays and pointers. There is one way you know how to display values with an array. And if you have an array and you need to access items and display values, you use the square bracket. Let me remove all these. Let's say you have short numbers equals 10, 20, 30, 40, and 50. In order to display items in my array, I use the subscript notation or the square bracket notation. So I do numbers at, for example, position 0 and L. If I want to display the second one, I can do at position 1. So this is the array notation or the square bracket notation. And remember from previous sessions, if I display only the name of the array, then it's gonna display the address of the first item where the memory starts for the entire array. The memory starts at the first item. So this will display an address. So this can be stored in a pointer, but I'm not gonna go into it right now. Let me go just how the book does it. The book tries to tell you that the fact that number displays the first item, then numbers, since it's a memory address, plus 1 is different than saying 10 plus 1. 10 plus 1 is adding 1 to the value in that memory address. But memory address plus 1 means go to the next slot or go to the next item in the memory. So paint. The fact that this is short type, that means they each consume 2 slots. So I have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, etc. Let's say this memory starts at 1000. So 1000 is right there. My array is 5 items. Each are 2 bytes because short data type. So 3, 4, 5. 1, 2, 3, 4, 5. So the first item is at address 1000. The second item is at address 12, which is here. The third is here. The fourth is here. And the last item is here. So 1, 0, 4, 1, 0, 6, and 1, 0, 8. So this whole slot or whole block has 2 slots, 2 bytes, has the value 10 in it, 10. Then this has 20, this has 30 as whole, 2 bytes for each. So 2 bytes, 40 consuming 2 bytes, 50 consuming 2 bytes. So if I'm dereferencing and adding 1, Just like the previous example, I dereferenced my pointer and I added 10 to it. If I dereference this memory address and I add 1 to it, I would be adding 1 to the value 10. But without dereferencing, if I say 1000 as pointer or as array plus 1, that means go to the next item. This is why the compiler needs to know the data type with pointers. Remember, in computers, all memory addresses are of the same size, and that's why pointers are powerful, because you can point to any object or any data type with the same size of key, you can say. All memory addresses in the computer are of the same size. For example, 64 bytes. 64 bytes are from 0 to whatever, X. So whether you are storing a file, large file, small file, etc., you are grabbing a block of memory from 0 to X, which is the maximum for 64 bytes, as an example. You're grabbing a block of memory and putting the value of the beginning address in your pointer. So this is PTR. You're grabbing a value from 0 to X. This value 0 to X is always 64 bytes, whether it is actually 0 or the X. The size is 64, just like integers. Integers or unsigned integers, remember for our example, we gave it minus 1000 to plus 1000. If it's unsigned, that means it's from 0 to 2000. Memory addresses are unsigned. They start from memory address 0 to the maximum range. So whether the value in integer is actually 1 or 1999, 1 will consume 4 bytes and 199 will consume 4 bytes. So whether I'm at the beginning of the range or at the end of the range, I need the same size of bytes to store that value. Just like here, whether it's 10 or 50 or 1000 or 10,000 or 3 or 30,000, I always need 2 bytes. Similar case for memory addresses. In computers, whether you are at the beginning of the available memory or at the very end of the available memory, you will need 64 bytes to represent that memory address. So pointers will only consume 64 bytes to point to anything. Anything in the memory address can be pointed to using only 64 bytes. So back to my initial example, pointers are powerful because you can point to anything using only 64 bytes. Now, 64 bytes is also considered as an example because some systems pointers are 4 bytes. If older systems have shorter bus cables and memory addresses, so they didn't go all the way to 64. Let's say it's 4 bytes. Pointers consume only 4 bytes from 0 to some X. My memory addresses in my computer are 0 to whatever 4 bytes can hold as an unsigned. So if I need to pass a large variable between functions, instead of passing the entire object, copying it between files, let's say it's a 1 gigabyte file. Instead of passing 1 gigabyte file between my functions or my objects, I can pass only 4 bytes that point to that 1 gigabyte file. So making my program lighter in a way. So in here, when we do arithmetics with pointers or memory addresses, we are jumping to the next item. So notice this will display the address of the first item. This will display the address of the second item, not 10 plus 1. Same, this will display the first plus 2 items, so the third item. If I run, notice the addresses, they're gonna be 2 bytes different. This is 08, then you have 09 because each item consumes 2. So if I go here and I move this here, if 10 is at 08, that means it's consuming 08 and 09. In hexadecimal, after 9, we don't have 10. After 9, we have A. So then the second item, which is 0A, is consuming 0A, 0B. Then the third item is at C, D, and then E, F. Then we increment by 1 and we start over. So the fifth item is going to be at 1, 0. If I go back to my program and I stop this and I tell it continue to display them as series, now we can see it in a better fashion. So different addresses now because the compiler allocated different addresses. So 5.8, 5A, 5C, 5E now will increment and start over because the series has ended at F. This item 40 is at 5E and 5F, consuming 2 bytes. Then the second item is at 6061. So if I go back to my program, the address as is +1 means jumping over items. So if I do a relation between this notation and that notation, you're gonna see that arrays are pointers. Notice I can dereference, right? If I dereference this and then I surround or I wrap this address, right? It was displaying address. This was displaying an address, so I'm gonna wrap it with the parentheses. This alone was displaying an address, so I'm gonna surround it or wrap it with parentheses and dereference it. Remember dereference, what does? Dereferencing goes to that memory address and grabs or reads the value in that memory address. Again, if I surround and dereference, surround this address and dereference, surround this address and dereference, I will be displaying 10, 20, 30, 40, 50. This is an address and I'm dereferencing it. Then the address of the next item, dereferencing it. The address of the next item, dereferencing it, and so on and so forth. So it will display 10, 20, 30, 40, 50. The first 10, 20 are from this notation. So you have a square bracket notation and you have the pointer notation. This and this are equivalent. Then these two are equivalent. Then I can write down the equivalent for this and this and this. So 2, 3, 4. These are the sorry. These are the same. These are the same. These are the same. And these are the same. If I start over, 10, 10, 20, 20, 30, 30, 40, 40, 50, 50. And this is the relationship between arrays and pointers. An array, it turns out at the end of the day, an array is a pointer. What else do you need to know? Yeah, that's what basically the book is saying. This notation is called pointer notation. This is the bracket notation. They do the same thing. The bracket under the hood is doing this. And in future, in this course, in future sessions, you're going to learn how to write your own method for the bracket. Meaning, you can tell your variable or your object exactly what to do if some other function called the bracket. For example, imagine numbers is an object that has a size, a volume, height, width, name, color. Then you can write your own bracket for that object, and based on the number passed, for example, whether it's 0 or 1 or 2 or 3, you will display a specific member variable or attribute for that object. For example, if someone passes 0, I'm going to display the size. If someone passes 1, I'm going to display the width. If someone passes 3, I'm going to display my name. So something like that. You will define your own body or own functionality for this operator, and it's called operator overloading, and you're going to see it in classes. So the relationship between arrays and pointers concept: array names can be used as constant pointers, and pointers can be used as array names. You learn in chapter 7 that an array name without brackets and a subscript, which is this, actually represents the starting address of the array. This means that an array name is really a pointer. And then they draw some figures, how the memory address is in the memory. And then they show you in figure 9-6 how the pointer notation relates to the array notation. Then they go to topic 9.4, trying to tell you that you can do pointer arithmetics. With pointer variables, you can do arithmetics just like you do in with a normal variable. For example, say I have this array. I'm gonna keep it. It has these items. Then I have some pointer, short pointer LPTR. I'm gonna initialize it by saying it's null at this point. Then I'm gonna say, okay, my PTR is equal to numbers. Does that mean now LPTR is an array? No, it's not an array. It's still a pointer variable pointing to a short data type, but at this line, it will carry the address of the first item because the number name alone represents the address of the first item. So now if I see out PTR, we're gonna see the address. Then I'm gonna say, for example, int I equals 0, I less than 5 because I have 5, I plus plus. And on each iteration, I'm gonna dereference my pointer and display the value. Then I'm gonna say LPTR plus plus. Notice in my loop, I'm not manipulating PTR. It's only I from 0 to 5. So it's a loop that iterates 5 times. And I'm not checking against my pointer or numbers. It's just a loop that iterates 5 times. But the fact that I'm doing this will allow me to jump on the items. First time, it's going to display dereferencing the address of the first item. Then the fact that I incremented the address by 1, that means it's going to go to the next item, then the next item, and so on and so forth. So run. End line, yes. Reference and then add. Yeah, so run. Why it didn't execute? Oh, I have shift by 1 to the left instead of less than. So 10, 20, 30, 40, 50, and this is the address of the first item. Now notice if I do How do we want to do it? For example, start by saying numbers plus 4 means the address of the last item, and then decrement. It's going to display it in an opposite order: 50, 40, 30, 20, 10. And I can do plus 5, jump 5 items. I can do plus 10, minus 10, minus 5. Yeah, so this is what basically is the book trying to say. You can do arithmetics. Then topic 9.5, initializing pointers. You can initialize pointer using null pointer like this, or initialize it with a memory address from an existing variable, or an array name. And they mentioned that they can't be different data type. Float my float cannot be pointed at with an integer pointer. The pointer has to be the same data type, because arithmetics need to know how many bytes it needs to jump or skip. If this is an integer and you add 1 to it, it needs to know that 1 is 4 bytes. Jumping 1 means jump 4 bytes in memory. If you have short numbers, short data type for an array numbers, and then you use an integer and it jump by 1, shorts are consuming 2 bytes, but jumping by 1 will skip 4 bytes. So it's going to be illogical. So that's why the compilers tricked you to have it on the same data type. Then topic 9.6 asks you, tells you that pointers can be compared just by addresses. Of course, the address of the later is greater than the address of the earlier, and that's logical. If I can compare 2 pointers, but basically I would be comparing the memory address, not the values. If one address comes before another address in memory, the first address is considered less than the second. C++'s relational operators may be used to compare pointer values, and you can use all relational operators: less than or equal, equal, not equal, etc. Then they start by telling you that you can pass by pointers. So remember how passing by value work and passing by reference work. You can also pass by pointers, and it will behave the same exactly like passing by reference. Remember the difference between passing by reference and passing by value? Passing by value, the function can do anything with the parameter or the argument or the input, and it will not reflect in the caller function or the boss function because it was passed by copy. However, if you pass by reference, anything that happens to the value of that parameter or that input or that argument will be reflected in the boss function or the caller function. Similar to pass by reference, you can pass by pointer, and anything you do in that memory address will be reflected in the caller or boss function. How do I pass by function? It's simple. We create a function. For example, let's say this is my pointer, and then I grab this and I say display what? LPTR. So I have a function that doesn't return anything. It's called display, and it takes short pointer, right? Then I define it by saying, hey, you see the function declared above, it takes a input. It takes a short pointer called input, and it does this: a input plus plus. If I run, I'm gonna get the same behavior: 10, 20, 30, 40, 50. So I was able to access the memory using the pointer and then iterate. Notice now, I display, and after displaying, I'm gonna dereference a input and add 1 to it. See the difference between this and this? These are two different statements. They do different things. This will increment 1 to the address. This will increment 1 to the value that this address is pointing to. So this is an address. I dereference the address, means go to the value inside that address, wrap it, and add 1 to it. So add 1 to the value stored in this memory address. This is different. This is add 1 to this address, means now you're pointing at this slot, go point to the next, sorry, not slot. You're pointing at this item, go point to the next item, whether it's 1 byte or 4 bytes or 10 bytes or 15 bytes. What I want to show you is when we go back to this caller method and I display again, you're going to see that the value has changed. I'm not going to increment here. I just want to jump. So display will manipulate the data, and you're going to see that the caller function, main function, reflects that change because pointers are similar behavior to pass by reference. So go, it will display 10, 20, 30, 40, but on each iteration, it added 1 under the hood. Then in main, it reflected that change. Oh, the address at the first item now has the old value plus 1, the old value plus 1, the old value plus 1, because passing by pointer behaves the same as passing by reference. Then they go to the last, I think that's the last topic before dynamic memory allocation, which is in future, after test 1. We are not going to do dynamic memory allocation today. So this is the last topic. And they try to explain that there are 4 types of pointers. 4 types of pointers. You're going to have variable pointer to variable value, or variable pointer to const value, or const pointer to variable value, or const pointer to const value. So what are these 4 types? These 4 types are just how they sound. Variable pointer to variable value. Variable pointer to variable value means it's a pointer that you can reassign addresses to it as many as you want, and you can access or dereference it and change the value as many times as you want. Variable pointer to variable value. Then you have variable pointer to constant value. Means variable pointer means it means it's a variable that carries memory addresses, and you can give it a new memory addresses as many times as you want. However, you cannot dereference it and change the value because this pointer is pointing to constant values. Third type is constant pointer to variable values. Constant pointer to variable values means it's a pointer that carries one memory address only, and you cannot give it a new memory address. It points to one address and it will keep pointing to it. If you try to give it a new address, it's illegal and it's a syntax error and it won't compile. And it points to a variable value. So you cannot give it a new memory address, but you can dereference it and change the value as many times as you want. Then you have constant pointer to constant value. Means it's a pointer carrying one memory address only, and you cannot change it, and you cannot dereference it and change the value. The memory address in that pointer is constant, and it's pointing to a constant data in memory. This number itself, numbers as a name, is constant pointer to variable value. Numbers as is, like this, see out, numbers, this as is constant pointer to variable value. Why constant pointer to variable value? Because I cannot give it a new address. It's illegal. it's gonna say expression must be modifiable L value. I cannot give it a new value. It's a constant pointer. However, I can dereference it and change its value. So it's a constant pointer pointing to a variable value. Whatever it's pointing to, which is the first item, whatever it's pointing to is variable value. You can access it, change it, do whatever you want, but you cannot change the address it's holding or it's carrying. So numbers or all arrays are constant pointer to variable values. So let's go over each type and show you the syntax. So variable pointer to variable is just anything like you have seen. So this is a variable value to, for example, I'm gonna give it the address of the third item. Boom. Right? This is a value at the third item using the square bracket notation, and I'm referencing it. I'm telling my compiler, give me the reference of the value stored in memory here. And it will grab the memory address and store it here. The same fashion I could have done by saying, hey, you see numbers? You see the address numbers? Jump 2 items and give me the reference of it. Or without the thing. So give me, so this and the previous are equivalent. This is right now, LPTR is a variable pointer to a variable value. I can go to LPTR again and give it a new address. It's not constant. I can say this time I want to carry this address. This time I want to carry this address. This time I want to carry this address. So it's a variable pointer. I can reassign memory addresses to it. I can give it one address, then I can give it a different address, etc. I can also dereference it and give it values. So it's variable pointer. I can give it a different memory addresses pointing to variable value. I can dereference it and give it different values. Variable pointer to variable value. Then we have variable pointer. So if you want to take a print screen or whatever, then we have a variable pointer copy to constant value. In order to specify that it's a constant value, C short, I'm specifying the data type. I specify it as const short. See how the errors popped up? The fact that it's a variable pointer pointing to a constant value, I cannot dereference it and change the value. It's created or declared as pointing to constant value, means nobody can dereference it and change that value that the pointer is pointing to. The error will say, hey, you're not allowed to do that. Expression must be modifiable L value. So this is the syntax for creating variable pointer to constant value. Instead of specifying short, you specify it as const short. If you want to take print screen, then we have constant pointer to variable value. Const pointer to variable value means this is variable value, right? Instead of short, now it's instead of const short, it's short. However, it's a const pointer. So the const now go between, oh, sorry, not here. After the asterisk. Oops, const. So it's a const pointer or to variable value. So the value is variable. The data type is not const. However, the pointer is const. It might be a little confusing, but you will get used to it. Now notice the errors. The errors popped up by saying you can, since it's variable, since it's pointing to a variable value, you can dereference and do whatever you want with the value. However, once you give the pointer one memory address, you cannot give it a different memory address. This pointer will carry one and only one memory address because it's defined to be constant pointer. Remember the example numbers? Numbers was created as an array. That means it's constant pointer to variable value. And the fact that I gave it a memory address, which is the address of 10, then doesn't allow me to give it any other memory address. For example, equals the address of numbers at 4. The fact that this is an array means that's a constant pointer to variable value. Means once I give it an address, I cannot give it a different address. Same fashion here. Once I gave it an address, I can no longer give it an address. But I can dereference it and change the values. If you want to take print screen, short, asterisk, const. Then we reach to constant pointer to constant value. And that is const short asterisk const. This is constant pointer to constant value. Means once you give it an address, you cannot change it and you cannot dereference and change the value. So this has to be modifiable and this has to be modifiable. Const to const. Why these are important? Because sometimes you work with code that you didn't write, or you collaborate with other teams, or you want to protect yourself from yourself. So even if you are writing the code for the entire program, you still need to protect your code from your own mistakes. For example, if I have a function that and remember in functions, every function, like I noticed in your assignments, that for example, you have a function that says pick a card or shuffle cards or whatever. You have a function that says pick a card. However, in that function, you are displaying. So that's not the right way to follow. It's not a good habit. Every function, the standard is every function should have only one job and one job only. And the name should reflect that job or that responsibility. So every worker function should have only one job and the name should reflect that job. For example, if you have a function that says pick a card, then that function should only pick a card, not display, not pick and display. So do not have a name different than the responsibility, even if you have only one responsibility. Also, do not have a function that have more than one responsibility. What I'm trying to say is, if you have a function called pick a card, don't let that function to pick a card and display and do something else. Only pick a card, pick a card, return the value. If you want to display, have another function that is called display. So the more you do, the more you follow this standard or this habit, the clearer your code is and the easier it is to debug. You know why? Because if you run your program, if you have a display function and a pick function and you are following the standard, and then you run your program and you see something wrong on the display, then you know exactly where to go. If something is wrong on the display, then it's the display function because that's its responsibility. If something is wrong in picking a card, then you go to the pick a card method because that's its responsibility. So this way you are pinpointing problems in your code instead of having everything in one function or more than one responsibility in one function. Makes it harder for you to debug because, oh, okay, something wrong, let me go to that function and then start from top to bottom figuring it out. So back to this. Why would I have different data types? Because sometimes I want to display. If I have a function that its responsibility is to only display, why would I give it variable pointer to variable value? That responsibility is only to display. The responsibility is not to change values. So I pass a constant pointer to constant value because the responsibility is to only display. Here is a pointer you're not allowed to change, and it's pointing to const. You cannot dereference and change. Sometimes you want to pass const to const. Sometimes you want to pass const to variable. Means here is a pointer. Do not give it a new address. Don't let it point to something else, but you can do whatever you want in the data. So based on the business requirement or the logic of your application, you want to protect your code by choosing the right data type. And this is the end of chapter 9. So I have the book next to me. I'm on page 530, which is topic 9.8, dynamic memory allocation. Dynamic memory allocation as an idea is that your program will allocate and release memory on runtime before after compilation time. So if you remember from previous sessions, we declare variables with data types basically to tell the program how many memory do we need in bytes. For example, in case I declare an integer, I'm telling my memory for this holder or carrier, I need 4 bytes. And this should happen on compilation time, means before I start building my program. So that when my program runs, all the memory for that program is already allocated. However, you can have some flexibility, of course, through some STL containers, standard template library like vectors, maps, and we're going to go over them in chapter 17. Or you can do dynamic memory allocation using pointers. So this is the concept. The concept is variables may be created and destroyed while the program is running. You allocate new memory and you free up that memory. Then you allocate a new memory, you free up that memory. For example, if I had an array integers, notice the compiler before I start building my program asks me, hey, well, you need a size. I need to know. The compiler is saying I need to know how many bytes for this array I need to allocate. So in case I put 5, I solved it. In case I put L user input, means I need to ask the user input for a size. Also, the compiler is not gonna like it. For example, enter the size cn L user input. It doesn't like it. It says, hey, this needs to be constant and needs to be initialized on compilation time and not on running time. The fact that I'm asking the user, that means the program is running. So I cannot allocate memory using this way. What I need is 2 keywords, basically. The first keyword is a new. The second keyword is delete. For the new, I can use it for both variables and arrays. However, the delete for variables and delete with the square bracket for arrays. These are the main 2 keywords. These are the only keywords for dynamic memory allocation. Anytime you're dealing with dynamic memory allocation, you're gonna be counting on new, the calls for new, and the calls for delete. You're gonna call new to allocate memory, and then you're gonna call delete to release memory. And the rule of thumb is we should not keep any memory allocated. In case we use only new without delete, that means my program is allocating memory forever. It keeps allocating memory without freeing it up. So at some point, my hard disk is gonna get full, no more capacity to allocate, and then my computer will basically gets to be blocked. Basically, if I'm allocating memory and there is no free memory, then my program is not going to function as expected. So the rule of thumb is anytime you use a new, you need to use delete. The same number of calls for the new should be equal to the same number of calls for the delete. If I call a new 10 times, then my program should be calling delete also 10 times. Means every block of memory that my program allocated, my program should release it as well. I allocate some memory. Once I'm done with that memory, I should release it. I should not allocate a new memory before releasing the previous memory. So again, the rule of thumb is number of new calls should be equal to number of delete calls. And I'm saying calls, not statements, because I can have the keyword new within a loop. For example, if I have a loop and I have new call in it, let's say this goes from 1 to 10. Let's say it goes 10 times. Here I have only one statement for a new, but the total number of calls is 10. So I can't just say, oh, okay, I have only one new in my code. It's on only one line. I have only one new keyword, so I should only use one delete call. So no, the number of calls should be equal. If you're calling new 10 times, then you should call delete 10 times as well. Every variable you call the new on it, you should call delete on it as well. So let's demonstrate a little bit. These are the definitions or the notes for you. So traditionally, I can't do it. I should have it constant and initialized on compilation time. However, with the new keyword, I can now do exactly that. So what I can do is I can say, okay, I have a pointer to an integer and it's gonna point to some memory. That memory can be with a specific size or one item, exactly one item. So I take the input from the user and then I say I need pointer to an integer that points to integers, and it is new integer L user input. New int. So now what I told my compiler on runtime, after asking the user what I told my program, I told my program, go allocate memory, new memory for me. For the data type integer means 4 bytes every item, and I need this size of integers. So the total size would be the number of items multiplied by the size of each data type. So if the user enters 5 and I know that every integer is 4 bytes, then my integers will have 20 bytes in size. Now this will be accepted by my compiler. I can then tell the user, okay, enter next value. Cn into L integers at, for example, I. And I can do that. I can iterate based on the user input. So if the user entered 5, I will be iterating 5 times. Now that I iterated and populated this array, I'm going to iterate it again and this time see out it, just so we see what's in my array. What's the warning? How reading invalid data from integer. The readable size is 4 bytes, but 8 bytes may be read. That's fine. Run. So enter the size. I need 5. Then it's gonna iterate 5 times. 10, 20, 30, 40, 50. Now that it iterated 5 times, I iterated again and displayed them. So during the runtime, while the program was running, I allocated memory and I populated them and then I accessed them. But I forgot one thing. Right now, this program allocated memory for five integers, but it didn't release that memory. If I keep running this program over and over and over again, I'm gonna basically take over all the free memory in the system because I keep allocating without releasing. So I go back. Once my system is done, or my function is done, or my task is done, or the process is done, I should release the memory. So I can say delete as an array, because this time I'm deleting an array, not one single value. Delete integers. So this will release the memory. Then after that, the rule of thumb is to set it to be null. Always after deleting, set it to be null. This way, sometimes, and some compilers, some programs, if you run delete and then you run a new again, it just doesn't like it. Some programs and compilers would like the new call to be called on a null pointer or a new pointer. If there was a pointer that you used before and you're planning to call the new keyword again, you better set it to null before calling the new again. So this is just a good habit to have. Integer is allocated with scalar new with deleted array, but deleted with array. Well, yeah, that's exactly what I need. Why it's yeah, this is exactly what I need. Will it like it if I do this? Yeah, strange. Okay, so now if I run, nothing is gonna happen. Same. I need 4, 10, 20, 30, 40. It's gonna display. Oh. Retry. It's still running. Go. I need 5. Go. I need you to go all the way here. 10. Continue. 20, 30, 40, 50. Okay. So integer now has values. This is the address and this is the first item. Delete it. Let me think. Oh, you know what? This might be the problem. I think it understood it as a constructor instead of size. We need the square bracket, my bad. I need pointer to integers and the size is user input. So now it's gonna understand that it's an array. It's not a single value that has been constructed using this value. So now that I told it the size is 5, reading eval data from integers. Well, I'm reading into integers. The size is 4 byte, but 8 byte might be read. Okay. Is this still the same? Well, let's run it and see. The size is 5, 10, 20, 30, 40, 50. So now integers has 10 in it at that memory. Delete the entire array. Now, see, it has some junk. So I better set it to null. Now that it's set to null, I don't understand this question mark. Okay, so this was the idea of dynamic memory allocation. So I'm gonna do more practice just so you can understand fully the concept. I'm going through the book. So concept, the topic 9.8, it says dynamic memory allocation, page 530. Then it speaks about the concept. It gives you some examples on how to allocate with the new keyword. Then a graph, graph 911, figure 911. It shows you how there is a pool of unused memory, and then your program goes and grabs a chunk of the memory. Starts at address X up to Y, and then your program starts populating and accessing that chunk of memory. Once it's done, you call the delete, and then that chunk of memory that your program allocated will be released back to the pool of unused memory. That pool is managed by the operating system. Your program communicates, and every program communicates with the operating system, and then the operating system communicates between your program and the hardware. The operating system is basically the manager, the controller. It is the operator, the operating controller. So let's do the example in figure 9.14, which is about totals and average of sales amounts for a number of days. So there's a company, it has sales, and these sales are throughout the days. So notice we don't have any errors anymore. It was because of this square bracket. So I'm gonna take this off, and then I'm gonna do a simple example about a company with sales. So I'm gonna need a pointer to sales, and that's a single value. I need a pointer to total, and that's a single value as well. I need total. I need a pointer to an average, and that's a single value as well. And then I need the how many days, and maybe how many sales on total if we have more than one sale per day. So I'm gonna go ahead. I needed a double to be. First one is the sales, null PTR. I need the same for a total, and then an average. So total, average, and then I need int for days. I need int for count. Then I'm gonna start asking the user basically, how many days of sales without the end line, cn into l num of days. So l sales, l total, l average, l num of days, and then l count of sales. Now that I grabbed those, this will act as the array. This will act as a single value, and this will act as a single value. Single value, single value. In this case, if we are taking into consideration more than one sale per day, this is array to dynamically allocate memory. So how many days? I need this number of days. So let's go and allocate memory for that exact number of days. So I'm gonna say L sales equals new double, right? I have array of doubles. So I need a new double for this size. Now that my program on the runtime allocated this memory, I'm gonna start asking the user to enter uh, the sales in order. So I'm gonna say enter your sales. Now that I told the user, I'm gonna iterate from 0 to num of sales. How many days? Yeah, okay. So one sale every day. Then I'm gonna say cout day I plus 1, so day 1 on the first. So day 1, the user is gonna enter it. I'm gonna cin into whatever my array at this location. Then I'm gonna cout an end line. This should go over one by one, right? And boom, 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 yep. Now that I took from the user all the info, I can calculate the total in one loop. I can calculate the total in a different loop. Just for the sake of demonstrating and keeping things clear and separate, I'm gonna do it in a different loop. But I could have do it on the fly, right? Every time the user gives me a sale amount, I just add it to the total. I can recompute the average on the fly. But for now, I'm gonna keep it separate, just because we are under educational settings and explaining things. So now that I took those, I'm gonna say, okay, for I equals 0, I less than L number of days, which is basically the same loop. I'm gonna say L total plus equals, and this L total, I need it to be new. Okay, so L total is we don't need it as a pointer, as a matter of fact, and average, I don't need it. I only need the array to allocate. So I'm gonna say this starts from 0, and average as well starts from 0. And then here I can say L total plus equal, because it started from 0, plus equals sales on whatever this index or subscript it is on. Now that I have the total, I can calculate the average by saying L average, which is a double, equals L total, which is also a double, so I'm good on the casting, over L num of days. Now that I have the average, I'm gonna just see out the result. So I'm gonna say total is L total, and L, I'm gonna see out average is L average, and maybe because we're gonna have some doubles, so let's fix the precision. So I'm gonna say fixed and show me it as is, and 5 maybe, set precision, set press. So since it's not suggesting it for me, that means I need a library. Include IO manipulation. Yep. Now it should suggest it for me. So set precision. Here it is. Set precision, I need it to 3. Now that I did this and I finished my task, how many times did I call the new operator? I called my new operator only once. Here it is. I only called it once, and I called it on an array. So the same call for an array and variables, but the delete, it has a different syntax for an array. The fact that it's an array, I'm going to say delete with bracket L sales. Now that I deleted, I set it back to null PTR. Now I can run. So sales, it's null, total is 0, average is 0. I ended up not using this. So how many days of sales? I'm going to say 3, just so we are simple. Number of days is 3. So go ahead and allocate memory. Enter your sales up to 3. So day 1, I'm going to say 10. Day 2, I'm going to say 20. Day 3, I'm going to say, so we have, let's put it total to 60. So go. So now compute total. Now it's 60. Then average is 20 because 60 over 3. Now set it to fixed. Average is this. Total is this. Delete sales. So now it's deleted. Now it's null. And program finishes. Let's have some decimal points this time. Let me close all these. Don't need this too. Let's do again, but this time with some decimals. So 5, 13, 25, 40, 11, and 42. So now I have decimals, only 3 precision. Here's the total. Here is the average. 131 over 5 is 26.2. My program ended and I released the memory. Here you see this diagnostic tools. At some point, if I am allocating big memory, it's gonna show me here that you or your program basically is using this much of the CPU, this much of the memory, this much of etc. So at some point, if I keep calling new without calling delete, you're gonna see that the memory is increasing. Right now it's 823, but it's gonna be more than that, and it's gonna be increasing. And when I shut down my program, that memory did not get freed up. So operating system will not know about it, will think that the program still allocates it. It's similar to when you open the file without closing it. So when a task or a process opens the file without closing it, it denies all other usage or uses for the file from different processes. If a different process comes to open the file, it's going to be denied, and it's going to say the file is being used by some program or some process. So similar fashion, if my memory allocates memory, that memory is being used by my program. If some other program asks for memory, the operating system is not going to give it memory from my chunk. It's going to go to a pool of unallocated memory and give it some memory. If my program takes over all the pool of free memory, then no other process will work, and even my program in future will not work because no more free memory in the pool. So as much as dynamic memory allocation is important, deleting and releasing the memory is also important. This is pretty much it for dynamic memory allocation. Let me see the book. The book speaks about examples for dynamic memory allocation, just like how we mentioned. Then we go to topic 9.9, returning pointers from functions. I'm pretty sure you know how to return a pointer from a function, but there is a key point that I need to point out, which is remember the scoping rules for variables. If I create a local variable, once within the scope, this variable is only available within this scope and any inner scopes, but not outside the scope. For example, if I have another scope or a for loop with a scope, integer is available inside the inner scopes. I can use integer here. I can use integer in the for loop, but I cannot use integer outside the scope. And not just that, once this scope finishes, once the control is done executing, this variable will be destroyed, will get destructed. So if I have a method that says, for example, give me return anything. So int return anything. Return, I'm gonna create L integer, right? I'm gonna give it 5. And then I'm gonna return it. This will return a copy of an integer. By the time the control reaches this end here, L integer will be destroyed. So you basically returned, or I basically returned, a variable that is about to be destroyed. So be careful with this case or with this example. We do not want to return any variable that is about to be destroyed, especially with pointers. The only you should return a pointer from a function only if it is within 2 cases. The first case is you are returning a pointer that was passed to the function. If a pointer was passed to the function and then you did, or your function did some task, you're allowed to return that pointer. And the other case is a dynamically allocated pointer. So returning a dynamically allocated chunk of memory. Only in these 2 cases you are allowed, or it's fine to return a pointer. If you are returning a pointer that was passed to the function, or you are returning a dynamically allocated memory. For example, here is this, for example, and I have int L integer equal 5, L integer PTR equals the address of L integer, right? I'm constructing the bad example. So this is a bad example, semicolon, and then I'm returning this. Let's return a pointer. I'm returning this pointer. Now I'm gonna see out return anything. I wrap it and then I dereference it. So this will return a pointer, and then the outer scope will dereference that pointer to display something for me. Run. It might probably display 5, but that memory is not mine anymore. So that memory has been released this got destroyed, the value is still in the memory. Let me explain exactly what's happening. So I created an integer and I put 5 in it, and then I referenced that integer. So now this pointer is pointing to a memory that has 5 in it. When this scope finishes, this integer will be destroyed, this pointer will be destroyed. The value 5 will stay in the memory. There is no variable referencing it, there is no pointer referencing it, but the 5 is in the memory. The fact that these two got destroyed means the memory they were using became free, back to the pool. Yes, there is 5 in that memory slot, but that memory slot is free for some other process. Imagine between this section and this section, imagine there's a lot of codes. Let's say this was done and it's pending, right? This has been done and the value is ready, but your program is doing something else and it takes 10 minutes. And your program is allocating memory, other processes are running on that PC, and the value that the function returned is ready. However, during those 10 minutes, your operating system gave that slot, wherever 5 was, gave that slot to some other process. And then your cout came to use that slot. It's gonna say access denied and the program will crash. Another way to see that happening is by saying, for example, go here, right? Go here, and then I'm gonna say for int I equals 0, and I'm gonna go maybe million times. I less than 1 million, I plus plus. I'm gonna say at this point, cout 0. I need you to see out the value in this address. And after you do that, go to the next slot. So I'm gonna go over 1 million slots. Some slots are free and some slots are used by other memory. The program is gonna keep going over the free slots, and as soon as it hits a slot that is used by another process, it's gonna crash. See? Read access violation. Now I don't know at which slot, maybe 100. So notice, look, there are values from previous stuff. So this is my 5. Then I jump to the next one, junk. Next slot, junk, 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 junk. Oh, not a junk. Oh, not a junk. So there is a value in that slot that has been used in the past, and the process released it, but it didn't delete the value. It doesn't delete the value, but the slot becomes free. So, oh, here's another one. Here's another one. So I can find maybe clearer or nicer values, not just a junk. 0, for example, null. But at some point, I'm gonna reach a slot that is being used by another process, and it's not gonna allow me, and it's gonna crash my system. There is no way I can continue, especially in C++. In C++, if you have one error in your program, the entire program crashes. Unlike JavaScript, for example. In scripting languages, if a function fails, only that function fails, not the entire program. The entire program is not gonna crash. Only that function will fail and will return some junk. In C++, if one line fails anywhere in the program, the entire program fails. See, I cannot continue anymore. There is no way I can continue. So with this example, Notice how I was able to just go over memory and access them until I reached an allocated memory. Similar idea or similar concept or similar consequences can happen when I return a value or an integer or a pointer that is about to be destroyed. At this point, when cout happened, actually let's split them. Auto L result equals this, right? I split them. Imagine between this line and this line, there is 1,000 lines of codes equals to 10 processes, 10 tasks or processes. Or between this line and this line, I have 1,000 lines of codes. I'm doing 10 tasks between here and there. When this got executed, I have the value here, but the memory has been released because this has been destroyed because the scope ended. When the scope ended, these two got destroyed, but result is still pointing to that memory address. Result is still pointing to that memory address, and here I'm trying to access it. However, some of these tasks went ahead and allocated new memory, and the operating system gave it the address of result. Now that I'm trying to access that memory slot, it's not going to allow me and my system is going to crash. So back to this point, you never do this above. You only return pointers in these two cases. You only return pointers in case the pointer has been passed already to the function, or it was dynamically allocated chunk of memory. Why? Because if it was dynamically allocated and you did not call delete on it, that means it's still allocated for your system and it will never be deleted. I will never have this case if it was dynamically allocated memory, because with dynamically allocated memory, I am the programmer who controls when will this be freed. So the fact that it was declared within you, even when the scope ends, it's not gonna destroy it. It's not gonna free up that memory. So anytime in my program, I can still access it. Right before I exit, I delete L result, L result equals to null pointer just for the habit, and then I'm good to go. So this is safe. This is one of the cases. This is safe. I'm returning a new allocated memory that has copy of integer in it, 5. The scope ended, the memory is still allocated because I used the new and without using delete. Now I can do my 1,000 lines of code, I can do my 10 tasks, and it's guaranteed that the result is still allocated for my program. In case I access it, I will be allowed and it's not gonna be denied and my program is not gonna crash. Notice the delete is without bracket. Without a bracket because I'm not deleting an array, I'm deleting a single value. This is a single value constructed based on integer. However, if I tell it I need integer, L integer ptr array equal new int with a square bracket, now it's an array. So this one is a single value with a constructor. However, this one is an array of integers, no size yet. I can give it 5, I can give it 1, I can give it whatever I need. So this is what the topic was trying to say. If you didn't fully understand me, send me more questions, send me questions, and maybe read topic 9.9 if in case you still need more info. With that being said, The last topic is 9.10, speaks about using smart pointers instead of pointers. Starting C++ um, 2011, which is called C++ 11, they introduced something called smart pointers. And smart pointers do the same exact thing like pointers, dynamically allocated pointers, but the only difference is with the smart pointers, they clean after themselves. So the programmer doesn't need to actually delete the array or the pointer. Smart pointers will delete themselves after every use. Once the scope ends or the program shuts down, they clean themselves. And we have three types of smart pointers. We have unique pointer, shared pointer, and weak pointer. Unique pointer is basically a sole owner of a chunk of memory. Unique pointer, nobody else points at that memory but that pointer. You cannot find two unique pointers that can point to the same chunk of memory. And when a unique pointer goes out of scope, it automatically deallocates the memory. It automatically frees up the memory. Then you have shared pointer, which is like the opposite kind of unique pointer. Shared pointer means this pointer along with other pointers are pointing to the same memory. It can share ownership basically of that chunk of memory, and you can have multiple shared pointer, obviously multiple shared pointers pointing to the same memory. Similar to unique pointers, shared pointers will clean after themselves. And if you have multiple shared, it only cleans itself after the last shared pointer is about to be destroyed. Not when the first, let's say I have 3 pointers pointing to the same memory address. If the scope ends on the first one, it's fine. It's not gonna deallocate it because we still have shared pointers. If the second one gets destroyed, the program doesn't deallocate memory because we still have one pointing at it. So there is always a count in the background that keeps track of how many pointers are shared on this memory address. Once the last pointer is about to be destroyed and no more shared pointers are pointing at that memory allocation, only then it releases the memory. So we have unique pointers, shared pointers, and then we have weak pointers. Weak pointers are similar to shared pointers, but they are not taken into count. Means if I have one shared pointer and one weak pointer pointing at the same memory address, once the shared pointer is about to be destroyed, the memory gets released. Even if I still have a weak pointer pointing to it. And it's called weak because of that. It's not taken into count. Once all the shared pointers are destroyed, then the memory will be freed, even if I have 1 million weak pointers pointing at that memory address. So that's basically it for dynamically allocated memory. Let me see what the book still has to say. They have a case study, which is sorting an array. That's for you if you need to practice. And that's basically it. Nothing in the book. Yeah, okay. So for next time, where are we at? We are at next time, I think, structured data. So next time is, yeah, structured data. So this is next session, which is like Wednesday or Thursday. And homework is due midnight Sunday. And the project 2 is also midnight Sunday. Then on Monday, I'm gonna assign you homework 5 and project 3. So let me know if you need any help or you have any questions about pointers, specifically dynamically memory allocation.